So we're starting off on what is quite a long question with a relatively straightforward question when we're looking at nomenclature, although there's lots of different things you need to consider as you're going through. First of all, you need to identify what the longest carbon chain is. What I'm hoping you can see here is that it's 5. Within that 5 is a double bond and a carboxylic acid. I'm going to include the COOH as the start of my carbon chain because it's the priority functional group. So I've got here my carbon chain highlighted. I've got my oic acid. I've got my N for the alkene. My alkene is in the 2 position, so it's 2-enoic acid, and my total chain of 5 means that it's pent-2-N-oic acid. But we're not finished yet because we also have a side chain. And on the side chain, we can see here we've got the methyl. It's in the 2 position, so it's 2-methyl pent-2-N-oic acid. But we're still not done because what we have got here is a stereoisomer. We've got the double bond in the middle. Each of the carbons in the double bond has got 2 different groups coming from it. So we know that this is going to be E or Z. Now we take a look at the size of the components coming off the carbon, and we can see in this case that the H is on the bottom and the CH3 is on the bottom. So this one is going to be Z, Z, because those 2 with the lowest atomic number are below the carbons. So they're both on the same side below the carbons. We then take a little sidestep and we move into the ideal gas equation and some maths. Now, 5 marks, we're working out a mass of a particular component of this, P. 5 marks tells us there's quite a lot to consider. Going to start off by doing the equation for the combustion of C6H10O2, and I am balancing it. I always follow the same pattern when I'm doing combustion of a hydrocarbon. I balance the carbons, then I'll balance the hydrogens, and then I will balance the oxygens. So once I've done that and I get my 7.5 O2, I've got my first mark for that equation. Now, from there, I am going to start to fill in all of the data, and I'm going to take that, and I've highlighted it as you can see here, because this is going to allow me to work out N. My V, the 180, I've shown you how we've worked that out. It's the 335 cm cubed that you can see in the top paragraph, and we're decreasing to 155. So that means 180 cm cubed was used. Now from there, my second mark achieved, I'm going to put my figures in and I'm going to convert them. So I would always recommend you list them in this way and then systematically go through and think, do I need to change them? And here I needed to convert my kilopascals to pascals, I needed to convert my cm cubed to meters cubed, and I needed to convert my degrees Celsius to Kelvin. Once I've done that, I can take my ideal gas equation, I can rearrange to make N the subject, and I can see here by putting all of those figures in that I have got 7.632 by 10 to the minus 3 moles. Now my moles of P used, I'm going to use, because that was my CO2, I'm going to use my mole ratios here. My moles of P used is 1/6 of the moles of CO2 produced. So I get 1.272 by 10 to the minus 3 moles. And then once I've got my moles and I can get my MR, which is 114 for this particular component, for my C6H10O2, I can work out my mass, which is 0.145 grams. Now, don't make the mistake of ending there because you need to convert it to milligrams. And you can see there where you're going to pick the marks up to take you up to the 5 marks. If you get to 145 milligrams, you will get 5 out of 5. However, if you make a mistake and your working out isn't shown, it's far harder to be credited with those marks for the working out. Okay, moving on to 10.3. And we are now considering structure determination. So what do we know? We know that Q is cyclic. We have got its infrared and its carbon-13 NMR structure, or carbon-13 NMR spectrum. And from this, we need to know what its structure is, and we need to use both of those spectra so that we can justify it. Now, it makes sense to do the evidence first. I'm looking at the fact that figure 4 has got an OH acid peak. We've got that big bulging udder on the left hand side. It's the way that I will always look at it. And we can see from its position that it is an OH acid rather than an OH alcohol. On figure 5, on the carbon-13 NMR, we've got 4 different peaks. So we've got 4 different carbon environments. So from there, we've got to try to work out what the structure will be. Well, if I know that there's a COOH and I know it's cyclic, let's start by taking the COOH and having it branch off the chain. And you can see here that we have now got a cyclopentane chain with a COOH coming off. So we've got the right number of carbons. Have we got the right number of environments? Well, we've got one environment here in the COOH. We've got one environment here. And then we've got symmetry. So this and this, these two will have the same environment. So there's environment number 3, and it's the same for these two. So there is environment number 4. And continuing with structure determination and analysis of spectra. So the carbon-13 spectra of R and S show the same number of peaks. The spectra can be used to distinguish between the isomers. So we need to look at why. We need to give the number of peaks for each isomer as well. If we take a look, we can see that both have got 3 peaks. So there's the first mark straight away. I've highlighted what the environments are. We can see the 2 yellow, the 2 pink, and the 2 blue. But when we actually look at the spectra themselves, we can see that in R, there are 4 carbons that are next to a C double bonded to an O. So 4 carbons next to a C double bond O. S only has 2 of them. If we take that a step further forward, the R has 2 peaks in the range 20 to 50, whereas S only has 1 peak. So for that reason, we can see that there is a distinguishing feature between them. Looking now at hydrogen spectra, again, same number of peaks for R and S, but we can use the spectra to distinguish. So we're going to use the splitting pattern of the peaks this time. First of all, number of peaks. Again, I've highlighted them here. We can see that we've got 2 environments in each of these examples, and therefore we've got 2 peaks. R will have 2 singlets. And we can see why, because the singlets are when there are no neighbouring non-equivalent hydrogens. Now, these hydrogens are on a carbon next to a carbon with no hydrogen, so there's no splitting. These hydrogens are on a carbon which is bonded to an identical carbon. So we've got no splitting there because these hydrogens are not non-equivalent. So we end up with singlets there. However, in S, we've got our CH3. Those H's are next to a carbon with 2 H's, so they will split into a triplet. And the H's in the CH2 environment are next to a CH3, so they split into a quartet. Moving on, It is a big question. The action of heat on 5-hydroxyhexanoic acid can lead to two different products. On gentle heating, 5-hydroxyhexanoic acid loses water to form a cyclic compound. This is very much application of knowledge. Under different conditions, it can form a polyester. Draw the structure of T, draw the repeating unit of the polyester, and name the type of polymerization. So, I'm going to start off by drawing out the 5-hydroxyhexanoic acid so we can try to understand where we're going to get this condensation. And on this particular example, I can see that I've got the OH on the acid, which I'm going to lose, and I've got the H on the OH in the alcohol that I'm going to lose. Now, what I've then got to do is try to reason this out, that if that's where my water goes, I'm going to get a link from this carbon to this oxygen. And it's then simply a matter of drawing it out, and that's what we've got here. When we move on to the repeating unit of the polyester, again, we've got to really think about how we're going to draw this out. Similar idea, except here, the OH is going to be lost off one monomer, and the H from the OH is going to be lost off another monomer. So I end up with this structure. I've got my C double bond O, I've got my bond going off, ready to join the other one, and I've rejigged the where I've actually put the CH3 and the O, so I can do it in a neat horizontal line. So that's my repeating unit. The type of polymerization that we're looking for here, well, the big clue is that we are removing water. So that takes us to condensation polymerization. Almost there now at the end of a very long question. So we've got 10.7, we've got an isomer U. The polymer formed by U and the polymer formed by 5-hydroxyhexanoic acid both contain ester groups and can be hydrolyzed. Draw the repeating unit of the polymer formed by U. Justify the statement that although both polymer structures contain ester groups, the polymer formed by U is not biodegradable. And the repeating unit of the polymer formed by U is going to look like this. So I've redrawn it. You can see in green, I've redrawn my structure in the way that I would always draw the monomer for an addition polymer, whereby I start with my C double bond C in the middle and I have my 4 components coming off it. And that makes it so much easier to then reason out what the repeating unit will look like. From there, the justification for why this is not biodegradable is that we have got non-polar CC bonds and therefore they cannot be hydrolyzed. So that's what we're looking for the justification on this particular question.